Hi, welcome back. In steps 4 and 5, we are going to define model tuning parameters and train and evaluate the random forest model. Defining model tuning parameters is important because machine learning classifiers have at least one important parameter which controls the complexity of the model. In this lab, we will use the train control function from the current package to evaluate the effects of model tuning parameters on performance. The train control function will select the optimal model and estimate model performance. So here we are going to define the tuning parameters by specifying the method. In this case, we are going to use the repeated CV, which is the repeated cross-validation. We are going to specify the number to 10 and then the repeats to 10. Note that the method parameter controls the resampling method. Okay, so this is it contains the methods for resampling, such as the repeated cross-validation. The number parameters refers to the number of folds or the number for resampling iterations during the model run. The repeat parameter provides the sets of folds to compute repeated cross-validation. So here we are running 10-fold cross-validation and repeating it 10 times. All right, so we are just simply going to run this chunk of code. And then after that, we move on to step 5. So in step 5, we are going to train and evaluate the random forest model. So we are going to specify the model arguments as follows. So we are going to start with the time start. So this is just the setting the time, the clock, to start recording the time when we run the model. And then set seed is the same as we've done before. We simply want to repeat the same model runs when we run it again. So this is quite important, as I mentioned before. And then we are going to specify our model as follows. We will use the train function, and then the train function is going to take the response variable as the class as a function of the predictor variables. So predictor variables, we have got them from the training set. So this is where our sentinel-2 bands are. So remember, we created a training set where we extracted spectral reflectance values from the sentinel-2 bands. Right, we are going to use the random forest as our method of choice. And for the tune control, we are going to just use the fit control that we have specified in step 4. Right, and then for proximity, we are going to set it as true. So proximity simply means we are getting or measuring the distances between two observations. Right, for the fit best, we set it to false because we don't want only to get the best model, but we want to get all the models so that we can evaluate. If you set the fit best to true, you will only get the best model. For the local import, we set it to true. So here we want to get all the variable importance for each lane cover class. So we set it to true. And then we are going to set the return data to true. So we close our model with the process time. So this is the end time. So if you run this chunk of code, we are going to get our random forest model. Please note, this takes a bit of time depending on your computer specification and the amount of training data set that you have. So for my case on my computer, it took about 5 minutes. So I've already run my model. So next, let's check the random forest model of performance. So we are going to use the print function to do that. So if we run, okay, we can see the results. So here, the output shows that we have 1,149 samples from our training set. And then we used 9 predictor variables. That is band 2, band 3, band 4, band 5, band 6, band 7, band 8, band 11, and band 12. And we have the 6 land cover classes, which are bay areas, built up, cropland, grass open areas, water, and woodlands. And from our sampling, we see that we have the following sample size that have been created. So the first folder has got about 1034 sample points, the second 1036, the third 1033, and it goes on. Right. So let's check some of the sampling results. So from these ones, we can see that here we have information about the M-try, accuracy. This is overall accuracy, and then the kappa. We are going to ignore the kappa, so we are just going to talk about the M-try and the accuracy. So M-try, these are the randomly selected predictor variables at each split. Okay, so the model is telling us that the M-try 5, okay, M-try equals 5 has got the best, okay, model, which is about 78%. Okay, so let's display the random forest plot. Again, it's just showing us the information that we got from the previous run. So here, only 5 random selected predictor variables were selected here, right? And then this one have got the highest overall accuracy. So this is the best model. Right, so let's check now the parameters of the best model. So if we run this code, we see that the best model used 500 trees, and the number of predictor variables which were used at each split is 5. Okay, this is what we have said before. And then the out of the bag error estimate is 22.37%, which is quite high. And then we can, here we have the confusion matrix. So what we can quickly pick is the class errors. We can see that the bay areas and the cropland have got very high class errors. So this shows that our model is not going is not doing a good job. Okay, the model is performing very poorly. Right. So next, let's compute the variable importance. Okay, so we are going to use the variimport function. So if we run this model, sorry, this line of code, we get the following output. We can see that the grass open areas is got very high variable importance. In fact, most of the predictor variables contribute so much to the classification of the grass open areas. And interestingly, band 8 is missing in the woodlands class. Okay, this is shows some problems with the model, because band 8 is useful for discriminating vegetation. However, in this case, it is actually missing. So it means there's something wrong with our model. Okay, we'll have a look at this later. Right. So after computing the variable importance, we are going to prepare a confusion matrix. So first, we predict, okay, the then cover class based on the new test data. Okay, so this is the test data set which has not been used during the model construction. Remember, we split our training data into training data set, which is used for building the model, and then the testing data set, which is now we are going to use to check the performance of the random forest model. And then we are going to construct a confusion matrix. So let's run this line of code, and this is our results. So here we've got our confusion on error matrix statistics, and then we have the overall statistics, and then we have the land cover class statistics. So I'm not going to detail about explaining these statistics, but what we can see is that the overall accuracy is quite high. It's about 78.5%. Right. So next, we want now to produce our land cover map. So we do this by classifying the Sentinel-2 imagery using the random forest model that we have obtained. So here we are just going to predict the Sentinel-2 imagery using the random forest model. So remember, the RVARS object contains the Sentinel-2 imagery for our test site. Right, again, I'm not going to run this code because it takes a bit of time. So I've already run it, and after that, we want to display our lane cover map. So here we're going to use the level of plot function. So let's run this one. And here is our lane cover map. So we have our different lane cover classes: woodlands, water, grass, cropland, built up, and bare areas. Okay, you can clearly see that there are a lot of these red pixels showing bare areas in the northern part of the test site. And we also have some of these red pixels in the southwest part of the test site. And even the southern part of the test site also, we have a lot of this red pixel. So this clearly, they are not built up areas. These are just misclassifications. Okay, so this is interesting because our model accuracy is saying that the model is quite good. It's about 78%. However, when we look at the actual lane cover map, we see a lot of problems. Right. So this is one of the reasons why we need to run the explainable machine learning methods, so that we understand why we are getting this kind of results. Right. So after doing this, we want now to save this map so that we can visualize it in GIS software. So we are just going to use the write raster function, and then we take this object LCRF, which we have created previously, which has been predicted in the previous step, and then we are going to save it as img .img format, or you can save it as GeoTIFF. And then if we run this, this is going to be saved. You can visualize it in QGIS or any other GIS software. So thank you very much for watching this tutorial. Please subscribe to my channel so that you get notifications if I have a new tutorial. I see you in the next tutorial.